Greetings and welcome to When Construction Meets Blockchain and Smart Construction Objects as Blockchain Oracles. We're going to get into it, but before we do, just remind everyone that this is strictly for the educational entertainment purposes of this YouTube channel broadcast, not to be used, misused, abused, or misconstrued for anything legal, lawful, personal, private, business, tax, financial, or otherwise, so please don't do this at home. That said, let's get started. So this is actually based on a paper from Liu, Li, Zhu, Zhao, Wu, and Ye. Automation and Construction, a paper written in 2021 from the University of Hong Kong. But this is definitely at the leading edge where these technologies actually are placed into the real world. And we're going to see some real world examples here along with this presentation. So let's get started. Let's picture a massive construction project. Of course, this would be something in Hong Kong, right? Imagine a prefabricated housing project in Hong Kong, 5 residential towers, and a commercial center. The prefabricated modules, so these are made in a factory and then just somehow brought on site there and then put together in a modular construction. They're manufactured in Jiangsu province, over 1,500 miles away in mainland China. More than 20 different suppliers are involved, with over 200 workers active on the supply chain at peak. Now ask yourself, how does the project owner in Hong Kong know that a beam manufactured in Jiangsu actually meets the quality specifications? So there's some big construction beam that's going to be used in these housing projects, residential towers in Hong Kong. So they're off on this island, and they're trying to have this manufacturing being done in mainland China in Jiangsu, 1,500 miles away. Well, also ask yourself, when a truck carrying prefabricated modules breaks down or takes a wrong route, who is accountable? And who even knows it happened? So, does the driver know? Was he told to go down the wrong route? Who is responsible? Who is accountable? And how do we even know it happens? How does the driver even know he's taking a wrong route? And another question is, if product documentation travels on paper from factory to site, what stops someone from altering it along the way? We usually call these travelers, pieces of paper that would go along with the job. But what stops someone from altering them along the way? Product documentation on paper. And the fourth question here, when a dispute arises over whether a component was delivered on time, whose version of the events can be trusted? So, 4 key questions. How does a project owner know that the quality specifications are being met by the manufacturer? So we have some quality concerns. We have the logistics here of the truck carrying the prefabricated modules. Who's accountable if he takes a wrong route? Also, we have the documentation control. How are we preventing fraud or forgery along the way as documents travel from factory to site? And of course, what's our methods of dispute resolution? And how do we identify the actors that can be trusted or not when we're trying to resolve disputes? Okay, so a lot to unpack here. And trust me, this just gets by pretty quick here. We're going to get the dense stuff out of the way first, and then it'll be downhill from there, where you'll have a really deep understanding of these things. So this is really where the future is going in construction. And if we get on it now, then we'll really be aware of the things going on that affect everybody that lives in a civilization on a large scale. And believe me, this is how civilization is expanding. There's 3 root problems in construction supply chains. These questions point to deep, systemic issues that affect construction projects worldwide. The researchers identified 3 core problems that make construction supply chain management so difficult. First, lack of trust. Where did this steel beam actually come from? Was it really inspected? The product provenance, meaning the verifiable history and origin of a product, is extremely difficult to confirm across long supply chains. So some places are getting goods from or raw materials from certain areas, so as they're manufacturing these products, it's extremely difficult to confirm across long chain supply chains their origins, history. When inspection results are disputed, though, there is no neutral, tamper-proof record to settle the matter. So there's our lack of trust issues. We want to know if it was up to quality standards. Was it inspected? Is there some accountability to the quality grade? We also want to know about a verifiable history and origin of a product, so that chain of custody along the way. And when the inspection results are disputed, what is the method of resolving the matter? So then we have fragmentation. The stakeholders on a single project may be spread across different cities, provinces, or even countries. Each stage of the supply chain, the design, manufacturing, storage, shipping, and on-site assembly, is often handled by different organizations using different systems. Information gets siloed and lost between handoffs. So what we're saying here is that when there's so many stakeholders on a single project, and they're in different localities, and they're in different stages of a supply chain, whether they're in the stages of design, manufacturing, when they actually go from the design to the realization, then to the storage, where do you hold it until it can be shipped? And then when it's shipped, what about the on-site assembly? How linked are they to the design to know how to do the assembly correct? It's often handled by different organizations, and they're using different systems. So is a system for design the same as the one used for the on-site assembly instructions? Information gets siloed and lost between handoffs. So some of that design information isn't needed for storage, but it will be for that on-site assembly. Does it get transferred? Well, we have the discontinuity. Much of the critical data in construction supply chains is still conveyed on paper. Oh, and we know this. Manual records are slow to create, easily misplaced, and vulnerable to deliberate tampering. When a prefabricated beam leaves a factory with a paper quality certificate, there is no reliable way to guarantee that document reaches the job site unaltered, let alone even reaches it. Most important is to have the materials there when you have the crew. So missing a piece of paper can be something that might lead someone to be incentivized, perhaps, for deliberate tampering. Who knows? So you can see where these issues can arise and their root problems are. Now let's look at giving construction objects the ability to speak. Think about this, construction objects. We're going to dig into this. What if every beam, truck, crane, and worker on a construction project could automatically report what is happening to them in real time without anyone filling out a form? This idea is the essence of the Internet of Things, IoT. So I'm going to try and stray away from using too many of these acronyms and such, but we will be using them at points because some of these are very common, like IoT, the Internet of Things. So let's try to remember this one here, and I'll try to recite it as much as possible. The Internet of Things, physical objects equipped with sensors and connectivity that collect and transmit data without human intervention. So this is where we get into the 5G network is really designed for that Internet of Things. Researchers have developed a construction-specific version called Smart Construction Objects. Now we'll be using this a lot, the SCOs. That's what this presentation is about, is Smart Construction Objects. An SCO is any construction resource, a beam, a truck, a crane, or even a worker's smart vest. So here's that wearable technology, fitted with sensors and a processor, turning it into a device that can sense, communicate, and act on its own. What do you mean by act? How can a smart vest act on its own? It could tell you the worker just moved from one locale to another. Two practical sensor configurations were developed for this study. One for tracking shipments. A low energy GPS global positioning system sensor is embedded inside each prefabricated beam. It continuously broadcasts the beam's location as it travels from the factory to the construction site, creating a real-time geographic trail. Sounds great in theory. For production and assembly, multiple high-frequency sensors measure motion, temperature, vibration, and other environmental factors during factory production and on-site assembly. This captures the detailed conditions under which each component was made and installed. So, by measuring all these types of hazardous conditions and making sure that they are all maintained below a threshold during production, then there can be an assurance of quality. Okay, that's in theory, but what makes these smart objects special? The smart construction objects are not just passive sensors that record numbers. They have three core capabilities that set them apart and make them powerful enough to serve a larger role in the system, a role we will be explaining shortly. So let's look at awareness. Wow, so we talk about smart objects. Here's one of the three things is awareness. A smart construction object can sense and record what is happening to it and around it in real time. So in this way, it can even notice that there's other smart construction objects nearby and know where it's in, if it's in a warehouse, if it's on a site with a variety of different objects. And this is in real time. For example, a GPS sensor mounted on a prefabricated beam knows where it is at any given moment during transport. A camera in a factory knows the surface quality of a concrete pour. This awareness can be triggered by the specific event, such as a truck crossing a border checkpoint, by a policy rule, such as its temperature exceeding a safe limit, as I mentioned here, the threshold, or continuously as part of a workflow. So this is awareness of these smart construction objects. The amazing thing is that these are almost, again, autonomous type of machines working, but only doing very limited specific tasks. There's also the communicativeness. A smart construction object can share the information it gathers, not just store it. It can respond when asked for data, the pull mode, so they can be interrogated. So this smart construction object, not just storing data, what it stores, it can respond when asked for that data. That's called the pull mode. So we're pulling the data from it. Proactively send updates on a schedule. Or when something changes, that's the push mode. So it crosses a critical threshold, it can push, hey, I just crossed a temperature threshold. Or make data continuously available for immediate access, so in a stream. The communication happens over wireless channels such as Wi-Fi, Bluetooth, cellular, 5G, or specialized protocols like Zigbee for short-range industrial use. And, as we spoke, the autonomy. Smart construction object can do more than just report data. It can act on predefined rules without waiting for a human to intervene. In passive mode, it assists human decision-making upon request. In active mode, it independently triggers actions when conditions change. For example, alerting a site manager the moment a shipment deviates from its planned route, or flagging a quality reading that falls outside acceptable tolerances. So, so if the shipment guy deviates from his planned route, They immediately get on the phone. Hey, where are you going? All right. Then we have the blockchain. That's the shared record that nobody controls. So this is an interesting concept here. The decentralized ledger. Imagine a notebook that every participant in a construction project holds an identical copy of. Whenever something important happens, a beam passes inspection, a payment is approved, a delivery arrives. The event is written into every copy at the same time. No single person can erase or alter what was written without everyone else's copies showing the change. That, in essence, is blockchain. 3 features make blockchain useful for construction. One is the tamper-proof records. Once data is written to a blockchain, it cannot be secretly changed. Cryptographic hashing, a mathematical technique that creates a unique digital fingerprint for each block of data, makes any alteration detectable to all participants. This is what gives the data its immutability. So this is something that allows the records, unlike the paper copies, can't be altered. Then there's the distributed storage. The data is not stored on one company server. Every participant maintains their own copy of the complete record. Or it could be stored in a cloud. This means no single party can withhold, manipulate, or lose the data because every other participant has the same information. So it could repropagate. And agreed upon rules. Before any new record is added, all participants must agree it is valid through a process called the consensus mechanism. We'll be getting into that. Think of it as a group vote that happens automatically. Every new entry must pass this check before it becomes permanent. So there's rules to keep it, as we said here. It's not that you can't write bad data, it's that you could tell it's been altered. Everyone else will see the changes so it can be ignored. All right, so let's look at the smart contracts. Smart contract. Oh, before we go any further, I just want to remind everyone that we do have the talking chat enabled, I believe. So if you have any questions, comments, clarifications, or anything else you wanted to add, you can just type it in the chat.
The tribe says, hit the like.
Yes, indeed, and it shall read it back, and then we'll be able to address those comments as we go along. And let's move along. So, smart contracts, the automatic enforcers. A smart contract is a set of rules written into the blockchain that executes automatically when certain conditions are met on an if this happens, then do that basis without any human intermediary. So this is where that trustless element comes in. Rules are written into the blockchain. These can't be changed or altered, and they execute automatically, so without any human intervention. A construction example. Consider a prefabricated beam traveling from a factory in Jiangsu to a construction site in Hong Kong. A GPS sensor embedded in the beam continuously reports its location. The smart contract contains a rule. Here's our rule. If the beam's GPS coordinates show it has arrived at the Hong Kong construction site, then update its status on the blockchain from in transit to delivered and notify the project owner. When the beam crosses the geofence around the site, which is either the coordinates that are pre-programmed into it that relate to that site, or perhaps there is some other signal that's broadcasted to that smart component, the smart contract fires automatically. No phone call, no email, no paperwork. So there it is. It has an embedded sensor. When that sensor crosses a certain area, then it automatically, somewhere, is going to pick up the signal that that sensor has passed that location. It's either going to push it out, or something's got to pull it from it at that site, get it onto the blockchain. At the point it reaches the blockchain, then this is all theoretical at this point. We're going to show exactly how this happens. At the point that it's either crossed that threshold, it's been pushed or pulled that signal that the beam has arrived, then it will send that information onto the blockchain. And when it gets to the blockchain, the smart contract is activated. The smart contract then, within its code, changes the status of that beam from in transit to delivered, and automatically sends a notification, either email, etc., to the project owner or whoever is designated to receive that information. This all happens automatically, so you could just see how this could be scaled. Now, again, we haven't gotten to all the issues that go along, but just this is the ideal scenario. So follow me on this. The researchers have already explored smart contracts in construction for payment security, automating the milestone-based payments when verified conditions are met, reducing disputes over when payment is due. Oh yeah. Then we have the quality management. We saw examples here already. Recording inspection results in real time. So all parties share the same quality data. They know that origin, they know the history of everything that's happened with it. Then there's component traceability, tracking each prefabricated element from factory to installation, so its history is verifiable. Then there's the BIM data audit. Okay, BIM stands for Building Information Modeling. It's a digital model of a building's design. So this is the data, and this is an audit. Smart contracts can record every change made to a BIM file, creating an audit trail. Nice. And then there's project delivery, managing the financial transactions of integrated project delivery, where parties share risks and rewards. Wow. So this is something where enough faith is put into that system where both parties will share the risks and, of course, the rewards for not having to have intermediaries, to pay intermediaries. Okay, now let's look at the missing link. How does real-world data get in? So here's a fundamental challenge. A blockchain and its smart contracts live in a self-contained digital world. They have no eyes, no ears, no sensors. By themselves, they cannot know that a beam has arrived, that a truck has crossed a border, or that a concrete pour met quality standards. They can only act on data that someone or something delivers to them. So they're on that blockchain network. Nothing's going to change with them until someone or something delivers it to them. The bridge between the physical world and the digital blockchain is called an oracle, borrowed from the ancient Greece. The term refers to any trusted intermediary that collects real-world information, verifies it, and delivers it to the blockchain for smart contracts to use. So, we're back where we started with intermediaries, aren't we? Just as you think that we're getting so it's a totally trustless system, it's not, but it's definitely minimizing trust along the way, where it's not reliant upon trusted parties, but to the system itself, the math and the lack of alterability and such. But we also have the fact that now we have to have trusted intermediaries. So this is the one link of trust that's still needed in the blockchain for it to function in the real world. And this pretty much is the heart of the matter here, whether you're talking about smart contracts, cryptocurrencies, etc. But we're going to really dig into this here, these oracles. The current oracle approaches have all significant weaknesses. There's human oracles. That's a person who manually enters data into the system. This is slow, interruptive, and prone to honest mistakes. And it also creates an opportunity for deliberate falsification. If the person entering the data has a financial interest in the outcome, the entire blockchain record can be corrupted from the start. Then we have software oracles. That's a digital interface or application programming interface. We see this a lot, APIs. So it's either a direct digital interface, or if it's using another, like let's say go from a bank account, draw from a bank account, the bank will have their application, and then they'll also provide the application programming interface, an API that feeds the data from an external database. But this reintroduces centralization. So you have a software oracle, that's the centralized type of interface. If the software source is controlled by one party, that party becomes a single point of vulnerability. The blockchain was supposed to eliminate exactly this kind of reliance on a single authority. Then we have hardware oracles. So where it gets a little interesting, as we'll see. It's a physical sensor that captures data directly. This is more objective than human input. But a lone sensor can malfunction, lose power, or be tampered with. Relying on one sensor is like relying on a single witness. If that witness is compromised, the entire record is unreliable. That's why I believe, if less supported by oath or affirmation, what witness says is one of the Bill of Rights. I believe is at the fourth. Or the fifth. But either way, I digress. Let's get back to oracles. Core vulnerability, the single point of failure. So this is the term here, single point of failure. You'll see this a lot also in aerospace and other types of critical types of engineering. Oracles are not a built-in feature of a blockchain. They do not benefit from the same consensus protections that make blockchain data tamper resistant. So again, these aren't working through those cryptographic algorithms. It creates a dangerous paradox. The entire blockchain system is only as trustworthy as the oracle feeding data into it. So we have the single point of failure problem, often abbreviated SPOF. All right. If a blockchain system depends on a single centralized data source, whether it is that one person, one sensor, or one software feed, then compromising that single source compromises every smart contract that relies on it. In construction, where data about quality, location, and safety has enormous financial and legal consequences, this vulnerability is unacceptable. The researchers describe the need for oracles with autonomous and decentralized computational power scattered in key construction processes. Think about this now. We're getting back to the Claude Shannon and the episode we did on the on that one there. I'm trying to remember the title of it. Give me just a moment here, and I'll pull it up. But it was one of the a very important one to watch on information theory, and I'll tell you which one it is. It could have been arrows in all directions. Is that the one? No, that was not that one. I know which one it was. It was, let's see here. Bear with me. If you haven't already, please hit the like. And if you want to see more things like this, then you definitely want to subscribe to the channel. And let's see here. Well, it was a good one. If you look through the playlist there, and it would be under the miscellaneous, I believe. And yeah, I think it was the struggle against randomness, I believe is the one. That's the one. The struggle against randomness. So if you look that one up on the playlist there, we'll see a little bit more about Claude Shannon and these specific information theory issues that are being dealt with here. So let's look at this. The single point of failure. depending on one single source, compromising the entire blockchain. So, in a construction process, they're looking for autonomous and decentralized computational power scattered in key construction processes. So, to look at this in the way a statistical model would, you look at this as being the power is scattered, decentralized computational power that's autonomous. So feeding the sensor data through a decentralized computational power scattered. What is the computational power? We're going to be looking into that, how we're computing. And this is just being a mathematical operation, what we're talking about here. That's decentralized, though, and autonomous. But another key word here is scattered. And in key construction processes. So we look at the ones that are most vulnerable, most critical, and the ones with the most enormous financial and legal consequences. Those are the key construction processes. And we want to scatter these autonomous and decentralized sensors that are, of course, going to have to be communicating with each other autonomously for that computational part we're going to get into in a moment. This is the central insight of the study here. The smart construction objects already sit at every critical point in the supply chain, on beams, on trucks, cranes, and workers. They already sense, communicate, and act. Instead of building a separate Oracle infrastructure, why not use the SCOs themselves as decentralized blockchain oracles? If multiple independent, smart construction objects all report the same data, their reports are cross-checked, the system can identify trustworthy data without depending on any single source. So by looking through this scattered, decentralized, but scattered in key construction process, meaning there's a method to the scattering and ensuring that there's more sensors in the more critical areas. So the prioritization of that in an orderly way, but it's done through a statistical modeling. This way we can identify trustworthy data and not depending on any single sensor because they are scattered. So let's see how this is actually implemented. All right, that's been a lot. Now we're going to look at how this is done. The solution, a 4-part framework. This is incredible. The researchers designed a system with 4 interlocking components. Think of them as concentric rings, from the physical job site outward to the stakeholders who need the data. There's the oracles pool. See, now we're going from oracles to an oracle pool. This is the registry of all available smart construction objects across the project. Stakeholders deploy the smart construction objects. So the stakeholders, these are the ones that are, of course, the project owners, whatever it is, they deploy the smart construction objects, which would be GPS sensors on beams, motion sensors on cranes, wearable devices on workers, and register them in a shared pool. So they deploy these SCOs in whatever format, whatever platform they come on. So it's not going to be any particular kind. There's just going to be many of them. And all the ones that are out there are registered in a shared pool. So each of them there'll be provisions to collect, push, or pull data from all of these sensors, regardless of where they're from. But that data is then taken into this shared pool. When a specific task needs data, such as tracking a shipment, the system randomly selects several SCOs from this pool using an unbiased lottery process, ensuring no one can handpick which devices provide data. So it's almost like a random spot check type of deal here. So you never know which one, if you figure you could just tamper one, there's a whole bunch in there and you don't know how many. So, and you don't even know which one's going to be chosen to be interrogated. So it makes it a lot more difficult to tamper with these devices or to destroy them or eliminate them. You never know how many there are because there needs to be no particular set number. So the pool through the computational models can make this selection process push and pull data appropriately in a way that uses these statistical ways of ensuring that there's a high degree of trustworthiness with these data. Then there's the Oracle sidechain. The selected smart construction objects form their own separate mini blockchain called a sidechain. So once it's selected a few and they've been qualified, there's a consensus reached. Then they can form their own sidechain. So this is all being done autonomously. Each SCO independently collects data, creates a digital fingerprint called a hash of that data, and submits it. Then there's this is in the sidechain, an aggregator smart contract. Oh my gosh. So there's a contract for the contracts. The aggregator smart contracts is another piece of code running on the system, and it's managing this pool of smart construction objects. The aggregator then cross-references all the submissions. If more than 51% of the selected SEOs report the same data, the system treats that data as authentic and scores each SEO's reliability. So if you don't agree with the 51%, then you'll get demerited. All right, so we see how that kind of works. You can find the sensors that are most reliable. Maybe some are damaged, some have low battery, maybe some were tampered with. And this way you could easily filter those out. So it's really a process of having a large sample and being able to filter to get rid of the noise and focus on the signal of correct data. So what a great solution here. Then there's, after the Oracle sidechain, that's a way of using what we had called the ASC, the aggregator smart contract. And it's managing all these smart construction objects within that Oracle pool. All right, then we get the service blockchain. So it's a 4-step. We're only on step 2. On step 3 is a service blockchain. This is the main blockchain that stores the verified, trusted records. A reputation smart contract. Oh gosh. So we get another one. It tracks each SEO's cumulative reliability score over time. That's your social credit score for your Oracle. The reputation smart contract tracks each smart construction object's cumulative reliability score over time and selects the winning. It selects a winning one, the winning smart construction object, the one with the highest reputation, to provide the official record. Over many rounds, reliable SEOs accumulate high scores, while faulty or tampered devices accumulate low ones, naturally weeding out bad actors. See how that works? Amazing. Then we have the stakeholder consensus. Before any of this operates, all the stakeholders, the project owner, contractor, manufacturer, and supplier. I don't know if any of these are smart contracts talking here, or what we call the decentralized autonomous organizations contributing, but I digress. So all these, a project owner, the contractor, manufacturer, and supplier must agree on which services to activate, which smart construction objects to deploy, and what rules to apply. Every smart contract and every registered smart construction object requires this collective sign-off before execution, ensuring no party can unilaterally control the process. So, until they don't need the people signing off, it seems like everything else, once constructed, once that consensus is reached for the stakeholders, everything goes into operation. So there's going to be a time where you have the robot CEOs making decisions with these smart contracts. Interesting. All right, let's continue. So let's follow a data request through the system. Let's imagine a site manager in Hong Kong, and he wants to know the real-time location of a batch of prefabricated beams currently being transported to Jiangsu. Here's what happens, step by step. The site manager submits a request through the service smart contract, which first checks whether this person has permissions to access the data. So The site manager, he has access to the service smart contract. Then the aggregator smart contract receives the approved request and asks the Oracle's smart contract to select SCOs from the pool. So he makes a request through the services smart contract. The smart contract rule says yes, the site manager, his request is approved, and he has permission to access the data. So bam, then it goes to the aggregator, and the aggregator smart contract gets the approval request, the approved request, I should say. And then it asks the Oracle smart contract, this is the one that keeps that pool, and of course their so-called credit score, to sort of reputation, to select smart construction objects from that pool. Then the Oracle's smart contract runs unbiased random lottery and selects 3 or more, see 3's a magic number here, GPS equipped beams to serve as independent data sources. So it picks 3 random from that pool, but unbiased. Now each selected beam's GPS sensor, their trust really hasn't been determined fully yet here. So each selected beam's GPS sensor independently hashes its location data and sends the hash back. The aggregator cross-references all responses. If more than 51% agree on the same location, that location is accepted as authentic. Now we get to weed out the bad actors. The smart construction objects that reported the correct location receive a reputation score of 100. Those that reported different data receive a score of 0. These scores are tracked over time by the reputation smart contract. That's the credit score there. Then the smart construction object with the highest cumulative reputation score is selected as the winner, and its full location data is delivered to the site manager through the service smart contract. So the service smart contract gives this guy access to the data, the site manager. And the data he gets has to go through this whole chain here so that it can be assured that it's the winning SCO or smart construction object, sensor, whatever it may be, Oracle, and its full location data now can be delivered with confidence. Whew. Of course, he doesn't see any of this going on. So what makes this system possible in practice? Remote quality verification. So hang on one second. Okay, we're back. So we have remote quality verification. A contractor in Hong Kong can access real-time quality inspection data from a manufacturing plant in Jiangsu. So he's that's 1,500 miles away. He doesn't have to go there to inspect. He can inspect, see all these things coming out of the assembly, all passing inspection without relying on paper reports sent by the manufacturer. Deep cameras and laser scanners in the factory act as smart construction objects, capturing the smoothness and dimensions of formworks, the size and layout of steel reinforcing bars, concrete compactation quality or compaction quality, and the surface finish of completed products. So all those little cameras and lasers are giving feedback as these products are coming out from that factory. All this data is verified through the Oracle sidechain before it reaches the blockchain, giving remote stakeholders trustworthy quality records for every production step. So if any of the sensors there aren't agreeing on that sidechain there, they'll get weeded out. Then we have the end-to-end shipment tracking. Low-energy GPS sensors mounted inside prefabricated beams provide continuous proof of location throughout the supply chain. Because multiple sensors on beams shipped in the same vehicle independently report their positions. And again, These could be that were installed on the beam, third party. There could be someone else tracking them too. It really doesn't matter. As long as that data can get to that Oracle sidechain, then their data can be cross-referenced as a proof of location. The beam with the highest reputation score has its location data recorded on the blockchain. So it gets its data there on the blockchain as the true location, right? This means site managers can see in real time where every component is and making scheduled decisions based on verified, tamper-proof data rather than phone calls and estimates. So think of it like this. Yeah, they're relying on one beam, and that one beam relates to the other ones around it, and they may or may not have sensors on them, and those sensors may or may not agree with what's on that one beam. But because there's been a broad enough sampling of the data set, that trustworthiness of particular sensors can be determined. And the ones with the highest reliability are the ones that are picked. So from there, you just need the data from one that's considered the canonical location, so to speak, or this is the true location with the others all kind of referenced to because they're all in the same truck with that beam. So that's an interesting way to see how this has been solved here without having the centralized solutions. Now we have worker safety with privacy. Wearable devices, smart wristbands, vests, and helmets capture data about worker fatigue, unsafe motions, heartbeat, heat stress, and location. and, wow, they really care about their workers in China. However, broadcasting raw health data to a blockchain raises serious privacy concerns. The system addresses this using a technique called federated learning. Each smart construction object trains a safety model using its local data samples without sending the raw data itself. Only high-level safety insights, not individual health records, are stored on the blockchain. This protects worker privacy while still enabling safety monitoring. I don't buy that, but I don't think they care that much. Anyways, I think that's just there to appease us, but I digress. Let's look at some testing it in the real world, the Hong Kong case. To validate their framework, the researchers applied it to a real prefabricated housing project in Hong Kong. 5 high-rise residential towers. Now, we're not imagining this. This was actually validated. This was done. 5 high-rise residential towers surrounding a commercial center. Prefabricated beams were manufactured in mainland China, fitted with GPS sensors, and shipped to Hong Kong. The team focused on 9 specific beams labeled C1023 through C1031. Okay, is that 9? Okay, yeah, all right. From the same manufacturing batch, all transported on the same vehicle. All right, so we get 9 beams, same batch, same vehicle. Natural test. Because these beams travel together, they shall report the same GPS location at any given time. Any beam reporting a different location is either malfunctioning or has been tampered with. This created a natural test. Can the system identify the truthful beams and reject the liars? This is our natural test. So how do you know which one is true and which one's lying? So the authentic beams, 24, 29, 33 beams reporting their true GPS location. But there were 2 malicious beams, that 1025 and 1026. I have a feeling that Lee and Liu or one of those researchers there sabotaged those, just make the study work. Reporting falsified data, plus 4 offline beams simulating sensor failure. Okay, so they did 4 offline ones to simulate sensor failure, but there were 2 malicious ones, it looks like. All right, so 2 malicious and 4 offline, but they got 3 reporting their true GPS location. So the test parameters, 3 beams selected per request, a minimum for 51% majority. Now, as you see here, we know the ones that are reporting the true one and the ones that aren't. We got twice as many not reporting the true location. But now 3 of those are selected per request. There's a minimum for 51% majority. The system was tested at 100, 300, 500, and 1,000 data request cycles to evaluate a long-term reliability. Wow. So per request. So a lot of testing goes on here. Let's see how that works out though. So how it was built, the technical platform. The prototype was implemented on a Hyperledger Fabric version 2.2, a permissioned blockchain platform. Unlike public blockchains such as Bitcoin, where anyone can join, a permissioned blockchain only allows pre-approved participants. This is appropriate for construction, where the parties are known and the data is commercially sensitive. So 4 organizations participated, each representing a real stakeholder role. We had the owner, acts as the ordering authority. In blockchain terms, the owner runs the ordering service that sequences all transactions. In construction terms, this is the project client who initiates and funds the work. So the owner is the one bankrolling the project. Then we have the contractor, the general contractor on the project. They participate in consensus, meaning they must verify and approve data and coordinate on-site assembly activities. And then we have the manufacturer, the factory producing the prefabricated components in this study, of course. They contribute quality and production data from their facilities in mainland China. And then, of course, the supplier, the material suppliers feeding into the manufacturing process. They provide data on the raw materials, origins, and specifications. Are they using the right kind of steel manufacturing it and all this? Well, we're going to know because we'll have all those quality records from the supplier, not in paper form that could be lost from the manufacturer, but we'll see it on the blockchain where it can't be altered. Each organization received cryptographic certificates, digital identity credentials, that prove who they are within the system. Every data entry, every vote, and every smart contract interaction is digitally signed, creating a verifiable chain of accountability. All right, let's look at the 4 smart contracts and what each one does. So is everyone still here with me? You'll see that the services smart contract is the gatekeeper. This is the contract as the front door. When a stakeholder requests data, say the current location of beams in transit, this contract first checks whether that person has permission to access the information. If it's approved, it packages the request into a signed digital token containing the requester's identity, the address of available smart construction objects, and the number of data sources needed. It then forwards this token onward. So that token appears on the blockchain and triggers our next event. We have the aggregator smart contracts. It's the cross checker. This contract sits at the center, coordinating everything. It receives the approved request that we just got from this service smart contract. It triggers the random selection of the smart construction objects. This is where it's going to do that percentage, 51% has to be in agreement there to make it to the reputation. All right, those collects their data, it performs a critical cross-referencing step. It compares all the responses and applies a simple majority rule. If more than 51% of the selected SCOs report the same data, those smart construction objects receive a perfect reputation score of 100, while those reporting different results get 0. If no majority exists, the round is repeated. Okay. So that's why you always want to have that odd number. All right, then we have Oracle smart contracts, the fair lottery. This contract manages the random selection of which smart construction objects will provide data for each request. So the Oracle's smart contract is the one that runs the lottery. So the aggregator cross-checks it. The Oracle's smart contract runs the selection here. It manages a random selection of which smart construction objects will provide the data for each request. It uses a cryptographic technique called a verifiable random function. essentially a mathematical lottery that produces provable random results. This ensures no stakeholder can rig the selection to favor their own sensors or exclude unfavorable ones. All right. So it's just a way of keeping it as random as possible. We know this doesn't truly exist, but it makes it essentially uh, so that nobody can rig it. All right. Now let's look at the reputation smart contract, the scorekeeper. This is the social credit score for the SCOs. So this contract, the reputation smart contract, maintains a running tally of every smart construction object's reliability over time. Each time a smart construction object is selected and reports data, its score is updated based on whether its report matched the majority. See, each time we have this aggregator doing his thing, he's checking to see if the ones that were picked by the lottery were more than 51%. Okay, so, and this guy's going to keep track of who's been naughty or nice. The SCOs with the highest cumulative score is chosen as the winner, whose data becomes the official blockchain record. Remember, the location, you can only have one location at any given time, so you have to pick one of them. Which one are we going to pick? We'll pick this one. Over many rounds, this naturally identifies the most trustworthy sensors. So you could even go a process of elimination over time with this scorekeeper here. And of course, this can come back to the aggregator here, or even the fair lottery, eliminate some from even being in the lottery here, and then just randomly pick from the ones that are functioning, so to speak. All right. And I think that's what we saw in our original example. So here's our results. Whew. I don't know how much you guys are really sticking with me on this, but we'll quickly look at what the chart shows. Across every test scenario, 100, 300, 500, 1,000 data requests, there are 3 authentic beams were the only ones ever selected as winners. The 2 malicious beams were never once selected, proving the system successfully screened out the tampered data. So let's break this down a little bit here. We also had the ones that had no data. There was 4 of them, right, that were producing no data, but we had 3 that we knew were good and 2 we knew were bad. So there's already a majority of good to bad here. And imagine if you had more bad ones than good ones. Then what does it do? Stop the whole supply chain? So the gray bars show ties, rounds where all 3 randomly selected beams reported different data. These ties confirm that each selection round is genuinely independent and random. All right, so we got authentic, authentic, no winner. And we can see how many times that, let's see here. They're the only ones ever selected as winner. Okay, so there it is. So each one of those was selected a certain number of times as winner for the number of data requests when they did 100. Here's for 300, 500, 1,000. So over time, these 2 look like the ones it really liked a lot. That's beam C1024 and beam C1030. I don't know why they didn't like 1029 as much, but they didn't. And that's quite a significant difference here with the 1,000. But I guess it's that's how the mathematical thing worked, and a lot less ties too. So interesting way to look at this. I don't know how many tests have done. This was one test that they ran this whole simulation through, but I'd like to see it with more failure points along the way and how it can accommodate failure points. As we see here, there's no single point of failure, but what if there is enough multiple failures to cause something to stop? But what if it's the mitigations? All right, now let's look at the results here, the reputation scores that track the reliability over time. And over 100 rounds of data repairs each authentic beam's cumulative reputation grows steadily. An interesting pattern. 1029 had the most wins out of 100 rounds, but the fewest in 1,000. Yeah, confirming the random lottery is fair over time, I guess. Or there's some other artifact mathematically in that selection process. The system builds a long-term reliability record for every sensor, much like a credit score tracks financial trustworthiness, much like. Important caveat, if malicious sensors ever outnumber honest ones and collude, the 51% rule, would accept their false data. However, the sidechain still records all data history for later audit. An important safeguard for dispute resolution. Well, yeah, good luck with that. Security and legal significance. So for legal professionals and regulators, the system's security properties have direct relevance to evidence integrity, data privacy, and accountability in construction disputes. There's confidentiality. The system uses separate data channels so that only authorized parties can access specific information. SCO sensor data is stored in a private database accessible only to designated participants such as project owner, and all data is encrypted using cryptographic hashes. This means that a competitor cannot view another party's inspection records, and sensitive work health data stays within appropriate boundaries. So we would want. All right, then we get the data integrity and non-repudiation. Each piece of exchange data is time-stamped and made tamper-proof. The transport layer security, TLS, is the same protection protocol that protects online banking, secures data in transit. The random selection process for the smart construction objects is also recorded in tamper-proof logs. For legal purposes, this means a party cannot later deny that a specific data submission was made, and the exact sequence of events is independently verifiable. Yeah, but in American courts, I'm not too sure what the evidentiary bar is for bringing this stuff in, because again, the decentralized nature of it makes it so there's no one that can actually testify for it. But I digress. Let's go on to the authentication here. Every participant holds a pair of cryptographic keys. A public key, shared openly as a digital identity, and a private key, kept secret, used to create digital signatures. Every action in the system is signed with a private key and verifiable with a corresponding public key. This creates a chain of accountability. You can prove exactly who submitted what data and when. So essentially, it's like this: if we both have a public key, and let's say it's just colors of ink, and our public key is yellow, and you can see it, and I can see it, everyone sees the yellow. But now I want to talk with you on this yellow channel, right? But we want to have a private key. Well, my private key, nobody knows what color my ink is. No one knows what color yours is. Neither do I know what colors yours is. But I'll put my color ink into the yellow and mix it up, and I'll pass it to you, and you'll put your color of ink into the mix I just did and mix it up. And now what we both have is something that can't be taken apart back to where it was without knowing what was in it to begin with on each part. So that becomes our private little keys to talk back and forth with. But that's done with numbers and math and very large prime numbers. All right, so let's look at the authorization here. A membership service provider controls who is allowed to do what within the system. So this is an interesting concept here too, the membership service provider. For example, a contract, or only authorized parties can trigger the smart contract functions. So again, this is the access of the oracles. For example, a contractor cannot unilaterally alter a manufacturer's quality data, and a supplier cannot access worker health records. These access controls are built into the blockchain architecture and not enforced by policy alone. All right. For those of you here, you need to stick to the end because there will be a special surprise at the end of this presentation. So stay tuned. So what this achieved and what remains to be done. What the study achieved. It demonstrated that smart construction objects, the devices that are already present in construction sites, can serve as decentralized blockchain oracles, removing the need for separate centralized data feeding system. This is because we have, again, those service smart contracts and Oracle smart contracts and reputation smart contracts and all those things. That allows us to use any already present smart construction objects, GPS locators, things like that, RFID tags. It proved through the Hong Kong case study that a network of multiple independent smart construction objects acting as a sidechain can avoid the single point of failure problem. When multiple sensors cross-check each other, tampered or faulty data is screened out. The cross-reference mechanism combined with the reputation scoring system effectively identified authentic data sources and built long-term reliability profiles for each smart construction object, a verifiable track record of trustworthiness. But they did acknowledge some of the limitations. The framework is conceptual and does not claim to solve all blockchain Oracle challenges. It provides a guideline, not a turnkey solution. Only the request response interaction pattern was tested. Two other patterns, publish and subscribe, which are continuous alerts, the stream as we spoke about earlier, and intermediate read, instant access, have not been implemented yet. The 51% majority threshold is vulnerable when few sensors are available. If malicious devices outnumber honest ones, false data could pass. The researchers recommend a flexible consensus range of 51% to 67%. Well, if you have fewer sensors, that's not going to help either. Deploying multiple redundant sensors increases costs. Performance measures like system speed, capacity, and scalability were not evaluated in this study. Now, that's probably the least limitation to worry about there. All right. So let's look at the bigger picture, turning the construction site itself into a trustworthy data source for blockchain. This study shows that the physical objects on a construction site, the beams, the trucks, the cranes, the worker safety gear, need not be passive. Equipped with the right sensors and connected through the right framework, they can become a decentralized network of witnesses, each independently reporting what is happening and cross-checking each other's accounts. The blockchain then becomes not just a record-keeping system, but a system backed by verifiable physical evidence. So you have record-keeping accuracy and real-world accuracy at the same rate. We have future research directions, which are extending the smart contracts to support continuous monitoring, the publish subscribe, and instant data access, the immediate read patterns. Developing a game theory-based reputation system that more dynamically rewards and penalizes the smart construction object behavior. Yeah, that 51% is kind of shifty. And testing additional services, including real-time production quality transparency and worker health and safety monitoring across multiple projects. Well, that's way down the line there. All right, so that takes us to the best part of the presentation where we get to the fun quiz. So here's how we play this quiz. On the chat, you put in the number of the question followed by your selected answer. So if this one I was going to go for question 1, I was going to take D. I'd put in the chat Arabic number 1 followed by letter D delta. That would be my choice. If I decide I want to change it, I just put the same number in again and then put the different selection of my choice. And that last answer will be the final answer and will be the one tallied up at the end when we test our knowledge. Let's get started. Question 1. A shady supplier swaps premium steel for a cheaper grade, and then doctors the paper certificate. Everyone in the office is fooled. So why does the job site itself blow the whistle? So everyone in the office is fooled. No one knows that they get swindled with the cheaper grade steel. So how does the job site itself blow the whistle on the shady supplier? Is it A, the blockchain somehow knows the difference between good and bad steel? Is it B, cameras and scanners at the factory already captured the real data and nobody asked their permission to lie? Then we have C, the smart contract emails a photo of every beam to the boss. Or D, an eagle-eyed IT intern was monitoring the supplier's database. So why does a job site, though, itself know that the supplier was putting in the bad steel? Anyone have a stab at this one? Is it because the blockchain somehow knows the difference between good and bad steel? Is it because cameras and scanners at the factory already captured the real data and nobody asked their permission to lie? Or is it because a smart contract emails a photo of every beam to the boss? Or is the eagle-eyed IT intern monitoring the supplier's database? Anyone want to take a chance at question 1? We get question 1 going once, going twice. On to question 2. All right, this was a little easier. Budget cuts. Management decides 2 GPS sensors per truck is good enough instead of 3. As we spoke about here, how do you get a majority when you only have 2? Well, a hacker knows this and he compromises one. What just happened? A, the blockchain shuts down and everyone goes home. B, relax. The reputation scores will sort it out eventually. C, now it's a coin flip. One sensor says X and the other says Y, and the 51% rule has no majority to break a tie. Or D, the system catches the mismatch and pages a human to investigate. So what's the correct answer for question 2? Was it takes the blockchain down and everyone just goes home? Is it the reputation smart contract will will sort it out and then fix it? Will it be a coin flip since there's no majority to break the tie? Or does the system catch a mismatch and pages a human to investigate? So what just happened when 2 on the truck and a hacker compromises 1? Is it A, B, C, or D? All right, question 2 going once, going twice. We're on to question 3. The beams are 3 days late, says the contractor. No, they weren't, says the manufacturer. It's a classic he said, she said. What makes this fight play out differently now with our smart construction objects? A, blockchain records are automatically admissible in every court on Earth. B, both sides are already committed to the same tamper-proof, time-stamped, sensor-verified record before they had any reason to argue. C, smart contract already docked the late party's pay, so the argument is moot. Or D, Hyperledger Fabric ships with a built-in judge. I'm not catching anyone's attention here, am I? All right. So what makes the fight play out when we have a he said, she said about beams arriving late? Is it because the blockchain records are automatically admissible on every court on Earth? Is it because both sides already committed to the same timestamp sensor verified record before they had any reason to argue? Is that why it plays out different now? Or is it because a smart contract already docked the party's pay, so the argument's moot? So the late party already got the penalty paid, which we saw before that smart contracts can do. Or is it the hyperledger? That's what they form these smart contracts with. Was it, or the smart construction objects? Was it? It ships with a built-in judge module, I would assume. All right, question 3, going once, going twice, going 3 times. Tough audience tonight. We're going on to question 4. The City Council loves this idea and wants to embed vibration sensors in a new bridge for round-the-clock safety monitoring. But a sharp engineer raises her hand. What's the catch? So, just going to say, but GPS sensors work great, but vibration sensors and blockchains don't mix? Or is it B, Hyperledger Fabric wasn't designed for public infrastructure? C, everything proven so far is ask and answer. Nobody has tested whether it works for the non-stop real-time alerts a bridge would need. Or D, the reputation scores update too slowly to catch a falling bridge sensor in time. So which one is it that the sharp engineer raises her hand about? They want to put vibration sensors for round-the-clock safety monitoring. Is it because the vibration sensors and blockchains don't mix? Is it because the unified modeling language here doesn't work with public infrastructure? Is it because everything proven so far is ask and answer? Nobody has tested whether it works for real time, non-stop alerts that the bridge would need, or because reputation scores update too slowly? All right, let's get on to the answers since no one's answering. Question 1, shady supplier swaps premium steel for cheaper grade, doctors the certificates. How are they caught by the job site? Well, cameras and scanners at the factory already captured the real data, and nobody asked their permission to lie. The sensors record independently and continuously. A forged paper certificate can't overrule what multiple devices already agreed they saw. So, there we go. Now we have budget cuts. Management decides 2 is enough instead of 3 sensors. Well, the correct answer is C. It's a coin flip now because if one sensor says X, the other says Y. The 51% rule has no majority to break a tie. 2 sensors that disagree means neither hits 51%. The system literally can't tell who's lying, bringing back the exact single point of failure the whole design system was built to kill. So there we go. We have to have more than 2. That's why I say 3 is the magic number. Then question 3. Beams were 3 days late, says a contractor. No, they weren't. Well, both sides already committed to the same tamper-proof time-stamp sensor-verified record before they had any reason to argue, so there's no reason to even have this fight. The fight shifts from whose story do you believe to what did the sensors, which both sides agreed to trust in advance, collectively record. Neither party can rewrite history, so that dispute goes out the door. And question 4. City Council loves the idea of the vibration sensors in the blockchain, but the bright engineer stands up and says, everything proven so far is ask and answer, so the correct answer was C. Nobody has tested whether it works for the non-stop real-time alerts a bridge would need. The bridge safety needs always-on alerts, publish, subscribe, not one of data pulls requests. That pattern was sketched on paper, but never actually built or tested. A big gap for life safety use. In other words, you don't want the sensor to be telling you the bridge is falling. You want to be able to predict it's about to and close it down before there's a disaster. All right, well, for those of you that did stay, thank you, and I hope you learned something about the future of construction and smart construction objects on the blockchain oracles. This is where the physical world meets the digital blockchain, and this is how a lot of business is being done now and will be done more so as time goes on. So just as anything else, it's good to know where things are going and where they are right now, and to follow the trends and to see the trends, because the trends are not just what we're doing now, but we'll be doing more of as time goes on. That said, thank you all for attending, and I hope to see you all on the next one. Peace out.